Pointing vector, I'm going to discuss about this theorem, and here the work done requires to assemble static charge distribution against Coulomb revulsion, and electrostatic we can write the work done as this is the electric work done, and already this equation we have calculated at the previous chapters, and the energy stored in an electric field, which is equal to epsilon r divided by 2 integral e square divided d tau, and where E as the resulting magnetic E as the resulting electric field. Similarly, the work requires to get current going against the back EMF and the energy stored. That means that the energy stored in the magnetic field, we have already know about this. 1 over 2 mu naught integral B square d tau. B is the resulting magnetic field. Then if we are talking about electromagnetic field, electrodynamics, then we can have electric field and magnetic field and electromagnetic wave. Then combinedly, we can write down the energy stored in electromagnetic field. If we add this and this both, then this will be the energy of the electromagnetic field, 1 over 2 epsilon naught E square plus 1 over mu naught B square d tau. So this equation is very, very important, and we want to explore this equation more generally and want to develop the energy conservation law of electrodynamics. To explain more generally this equation is, we suppose that we have charge and current configuration. Let's suppose we have this configuration and we have some charges in this volume V. Then it produces fields E and B. It has some electric and magnetic field. If at any next instant dt the charges move, if these charges start motion, if this is a charge, this start motion here, this is also start motion here, this start motion here, then the question is how much work dw is done by the electromagnetic forces acting on these charges and time dt. According to Lorentz force law, F dot dl, which is equal to, this is the Lorentz force law, and we know the Lorentz force law Q into E plus V cross B dot, this is the dl, which the charge displaced from one point to another. So this is dl, and dl we can also write down v d tau, v dt, because v is equal to s divided by t and s is equal to vt. If this is dl, then v dt. This we can write down dl is equal to v dot dt. And now multiply this v dt here, then q e dot v dt plus v cross b dot v dt. Okay, and then v dt, we can replace, we can shift the cross and dot product, then v cross v dot b d tau, then v cross v, which is equal to 0, and then q e dot v dt. And we also know about Q, because Q is equal to rho d tau, because rho, which is equal to charge per unit volume, d tau. Let's suppose d tau is a charge per unit volume. Then rho, this charge will be equal to rho d tau v dt, and then this d, okay, this d tau e dot rho v d tau, and this rho v, this is equal to j, and d tau e dot j dt. So this is actually dw, dw, and now this dw, which is equal to d tau dt, which is equal to e dot j. It means that this e dot j, this is equal to work done per unit volume per unit time. Or we can also say that dw divided by dt divided by d tau, which is equal to e dot j. Here dw divided by dt, this is power per unit volume, power per unit volume, which is equal to e dot j. So e dot j is nothing but it is a power per unit volume. And okay, this dw divided by dt, which is equal to e dot j and d tau for the whole, now the work done on all the charges. Now the work done on all the charges will be just, we can take the integration e dot j d tau, and let's suppose this is equation A. From this equation, we need to find e dot j. This thing we need. If we find out e dot j and then put in this equation, we can get the work done. So how we can find out e dot j? J, we can find out j from the Maxwell four equation, the Ampere's law with Maxwell's correction, and from this Maxwell's equation, we know that del cross B, which is equal to mu naught J plus mu naught epsilon naught partial E divided by partial T. And we need for this J, then it means that del cross B minus mu naught epsilon naught partial E divided by partial T, which is equal to mu naught J. And if we find J, then J will be equal to 1 over mu naught del cross B minus mu naught will cancel with mu naught, so epsilon naught partial E divided by partial T. So this value, now we will put this in this equation E dot J, then E dot J must be equal to E dot 1 over mu naught del cross B and epsilon naught partial E divided by partial T. Okay, and here E dot J, which is equal to 1 over mu naught E dot del cross B minus epsilon naught E dot partial E divided by partial T. In this equation, if you look to this equation, we need to find out E dot del cross B. And how we will find this? We will use the identity. Let's see. We will use the identity, and the identity is del dot A cross C, which is equal to C dot del cross A and minus A dot del cross C. This is a general identity. Now we have electric and magnetic field. Then we will put A and B, then del dot E cross B, which is equal to, this is B dot del cross E minus, this is E dot del cross B. If we compare, then E dot del cross B, E dot del cross B. So we need for this term, if we find this term, then E dot del cross B will be equal to B, and del cross E, this is the Faraday's law, minus partial B divided by partial T, and this term will go to this side, del E cross B. And now we must put the value of this in this equation. And further, this equation A, I will write down here, dw divided by dt, which is equal to E dot J d tau, and this is equation number A. Putting the value of this term here, then E dot J, which is equal to 1 over mu naught, and this term is minus B dot partial B divided by partial T minus del dot E cross B, and this term as well, E dot partial E divided by partial T. Further, this term and this term, we can represent these two terms as, this term I can write down 1 over 2 partial B square divided by partial T. If we differentiate this, then it will exactly the same of this. And also this term 1 over 2 and partial E square divided by partial T. Okay, then what we will have the situation E dot J, which is equal to 1 over mu naught minus 1 over 2 partial B square divided by partial T minus del dot E cross B minus epsilon naught divided by 2 partial E square divided by partial T. And if we look this term and this term, I can take some common and then I can represent like this. Minus 1 over 2, 1 over 2 is common, and partial divided by partial T is also common. Then I have 1 over mu naught B square plus epsilon naught E square. So this is, if we apply again, then this will be the same. And I have taken only the common. And minus 1 over mu naught del dot E cross B. So this is E dot J that I have calculated. Now putting the value of E dot J in this equation A. This is very simple because this is just a straightforward mathematics. Then putting the value of E dot J in equation A. It means that dw divided by dt, which is equal to integral this value minus 1 over 2 partial divided by partial t and 1 over mu naught b square plus epsilon naught e square minus 1 over mu naught del dot E cross B. And if I take the whole d tau, then we have two integrals. If we apply this integral to this and this, then these are two integral, volume integral, and it has minus 1 over 2 partial divided by partial t 1 over mu naught b square plus epsilon naught e square d tau, and minus integral of 1 over mu naught is common, and del dot E cross B and d tau. This is a volume integral, and this is the divergence of E cross B. We can use the divergence theorem, and this can be converted to the surface integral. So F using divergence theorem, then this term must have the form as minus 1 over 2 partial divided by partial t volume 1 over mu naught b square plus epsilon naught e square d tau, and apply the divergence theorem, then this can be converted to the surface and E cross B dot dA. So this is the divergence theorem. Now this is the final equation, d divided by dt, and it is the work energy theorem. It is the work energy theorem, and is known as the Poynting theorem. Okay, this is the final theorem, but what the first part shows and what is the second part gives us the information. Here, the first part, I will write down the first part of this divergence, this Poynting theorem. The first term shows that the energy stored an electric field. The first term shows that the energy is stored in electric field. Where the second part shows that the second part, this part, shows that the rate at which energy flow from volume V. And the negative sign shows the energy out from the surface. By electromagnetic field, by electromagnetic fields. The negative sign shows that the flow of energy is out from the surface. So this negative sign shows that the energy is out from the surface. As last time we have considered that we have, let's suppose I want to discuss this point as, because last time we have discussed that we have some surface that has some volume V and there are some charges. Then when it start motion, these charges, when it start motion, then the energy the energy decreases inside this volume. So this is the first part which the energy decreases inside, and this second part shows that whenever the energy goes out from this surface, and it also decreases. So this is the total work done in this system. So this is the statement of this Poynting theorem. This theorem states that the work done, this work done on the charges by electromagnetic force is equal to the work done on the charges is equal to the decrease in energy. This is the decrease in energy remaining in the field minus the energy that flowed out from the surface. So this is the statement of this Poynting theorem. As we have derived the Poynting theorem, and the last term, which is very important, and it shows that the energy per unit time per unit area transported by the fields, and this term is known as the Poynting vector. This term which is we already derived in the Poynting theorem, and this is denoted by S, and this is called the Poynting vector, the S dot dA. This is the energy flux density, because S is the energy transported and this area, so this term is the energy flux. And the final equation for the Poynting theorem, dW divided by dt, which is equal to UEM. This is the electromagnetic energy. I have labeled this by UEM minus S dot dA. So this is equation number C now. Further, we have the work done on charges will increase their mechanical energy, because we have some volume and there are some charges, and this whenever they move from one point to another point, then the mechanical energy will increase, and the mechanical energy will be in the form of potential energy or kinetic energy. So I have write on this, and let's suppose this work done, the mechanical work done, which is equal to d divided by dt integral of u mechanical d tau, and some volume. We already have considered some volume v, and there are some charges and there are some mechanical energy as well. Then the work done increases, d divided by dt, and this is the mechanical energy. Then from this equation C, the left hand side will be equal to this. It means that from equation C, we can say that this dW divided by dt, which is equal to this, then I will write down here, this is the d divided by dt and some volume, some mechanical energy, and d tau. So this is the equation now. And further, if I write down here the volume as well for this, and also use the divergence theorem back, then this equation C will take the form d divided by dt v u mechanical d tau plus d divided by dt ue m d tau, which is equal to, if we apply the divergence theorem back, then the volume and divergence of S d tau. And then what will be the situation now? This equation d divided by dt, if we take the integral, and this will be equal to mechanical energy plus electromagnetic energy d tau, which is equal to v divergence of S d tau. From here, if we remove the integral, then we have d divided by dt u mechanical plus u electromagnetical, which is equal to divergence of S. And this equation is very, very important. And this equation is known as the continuity equation for energy. Because if I compare this with the continuity equation for the charges, d rho divided by dt, which is equal to minus, I think we have some minus here, and divergence of J. Here, rho is the charge density. Let's compare this. Rho is the charge density. And here, U mechanical and U electrical, this is the mechanical energy density. This term is the mechanical and electromagnetic energy density. Here, this is a charge current density. This is the current density. But here S, this is the energy transport, flow of energy. This is the flow of energy, and this is the flow of charges. This occurs due to flow of charges. So these two equations are very resemblance with each other, because this is the continuity equation for the charge and this is the continuity equation for the energy, and these have a very, very close similarity, because this is the charge density, then this is a mechanical and electromagnetic energy density. This is the flow of energy and this is the flow of charges. So there is similarity between these two equations.